Hello, welcome to 3 Minutes Engineering Concepts. The idea of this channel is to explain any engineering concept within 3 minutes time. I will be able to explain any fundamental to advanced concept in mechanical engineering and material science. If you like the idea, then please subscribe to our channel and also share our videos and channel details to colleagues and students who can benefit from it. Thank you. Just to recap what we have covered until now, this slide shows you the kinematic equation which relates displacements with the strains. Next, it shows you the constitutive equation which relates stresses with the strains. And finally, the balance equations which is based on Newton's law, that is sum of all the forces should be equal to 0. These are the strong form of equations, so everything is satisfied in a very strong way. And as an analyst, the objective is to find the unknown field variables by solving these system of equations. And in this case, the field variable is displacement. So in order to convert the strong form of equations which were shown in the last slide, you need to use some kind of method to convert them into a weak form. And there are many different types of approaches as I discussed in the previous videos. And one of the approaches or principles which is known as Hamilton's principle is widely used principle to do so. And in this case, the Hamilton's principle in its integral form is given on this slide, where h is the Hamilton's function. And if you look closely, the Hamilton's function is related to kinetic energy T, potential energy pi, which is strain energy in our case, and also the work done by these forces. And the integral form of these kinetic energy, potential energy, and work done by different external forces were discussed in the last video, and their relationship in integral form are given by these three relationships at the bottom of the slide. So we have also discussed a very important ingredient of FEM, which is known as the shape functions. Shape functions are interpolation functions, as we discussed in the last video, well, a couple of videos before, and it describes the displacement through an element. If we know the displacement at the nodes, we can interpolate the displacement inside an element in simple terms. So in present case, we were using a 1D truss element, and we were dealing with that, so we had two nodes, and hence we had two interpolation functions. And in this course, we are only considering linear shape functions, so based on that, we basically derive the relationships for that. However, there could be higher order polynomials which can be used as shape functions, and again, you can look into other books and literature which discuss about that. So just for completion, shape functions, when you formulate those which are given on this slide, should satisfy a partition of unity. This means sum of the shape function at any location should be equals to 1, and also they are designed or derived in such a way that their value at their respective node is 1, while it is 0 at all the other nodes. So for example, if I have n1 and n2 in this slide as shape functions, then my shape function n1 should be 1 at node number 1, while it should be 0 at node number 2. And similarly, it will be for n2, my interpolation function will have a value of 1 at node 2, and it will be 0 at all the other nodes. And then we move to the next step where we said that, okay, how to formulate the FE equation in the local coordinate system. And if you remember, the equations were basically given by these relationships here, this equation here, and we then derived the relationship for the mass stiffness matrix, elemental stiffness matrix, mass matrix for an element, and the force vector, and they were all derived in local coordinate system. So the whole system of equations which is here and all the relationships for stiffness matrix, mass matrix, and force vector were in local coordinate system. In the last video, I also explained to you how to convert or transform your local coordinate equations into global coordinate system. And please bear in mind, these were all elemental equations, so it was basically meant to be for one element. So if you can look at the diagrams on the right hand side, what you see here is we can have in reality a structure which can have truss elements with different orientations. So this means every truss element can have a different local coordinate system, while your global coordinate system can be fixed around some axis. So in such cases you need to convert those, and I gave you a simple example where we said that the transformation matrix, which depends on the relationship between the local and global coordinate system, is given by this matrix, where Lij and Mij, I gave you this relationship for that, which depends on the direction cosines, and they were given by these relationships here. So once we know this transformation matrix, we can transform our elemental stiffness matrix, mass stiffness matrix, and force vector into global form using these relationships on the right hand side. Once we have done that, we can substitute it here, and we have an equation for each individual element. As you see here, in this case we have 3 elements, which is in the global coordinate system, and now it's very easy to assemble these finite element equations to form a global system of equations which has all the elements for the whole geometry. And that's what we're gonna briefly discuss today. So in today's video, I'm gonna briefly introduce you to three or four different things. Firstly, what could be the possibility for us to assemble the global system of equations, because until now we have been able to formulate the elemental equation, FE equations, in local and global coordinate system. Then the next step would be, if we have these differential equations, how we're going to solve it. And again, solving that equation depends on our boundary condition, our type of analysis we're going to do. So I'm going to explain those solving methods, keeping in mind, let's say if we are doing static analysis or dynamic analysis. So these will be the learning outcome for today's. Okay, so the first part is how to assemble and formulate global FE equations. Well, I'm not going to go into the details of everything at this point, but when we will be solving few numerical examples, things will be more clearer, because then we will be looking into individual vectors and matrices, and we will be assembling them together, so it will make more sense. But it's just the addition of the stiffness matrix, mass matrix, and force vectors at the equivalent nodes, which will be there throughout the whole model. And in this case, I mean, once we solve and formulate this, we will have basically a global system F equations which has all the elements into it. And so this will look something like this, where K and M are global acceptance matrix, mass matrix, while my D is the vector of all displacements at the nodes in the entire problem. So we're not looking at one element, but all the nodes. Let's say in the figure on the right hand side we have 3 nodes, so we will have all 3 nodes accommodated with all 3 elements in these equations. And obviously F is the force vector, which is of equivalent nodal force vectors depending on whatever forces are acting on each nodes. So as I told you during the previous videos, that the main aim of having those global or elemental F equations is, since it's a differential equation, so we need to look for some unknown field variables, and in this case our unknown field variable is displacements at the nodes. So the idea of the whole exercise is you formulate these global F equations, and then you solve them to find the unknown field variables. In this case, these are the displacements. Once we have found the displacements, solving these differential equations, we can use our constitutive equations and our kinematic equations to find out what are the values of strains and stresses in any element in the problem. However, to do so, we have to see what sort of analysis we are doing. So in our cases, there could be different possibilities. For example, we can be dealing with a static analysis where a structure is fixed and it has no rigid body motion, but it has forces acting onto it which can cause some kind of deformation. We can also be doing some analysis of free vibrations. This means our structure is under dynamic loading, and we need to find out what are the natural frequencies under those loading conditions to avoid any failure due to high amplitude of vibrations. Or we are looking at a transient response where a structure is under transient cyclic loading or some other type of loading which is varying with time. So all these different analysis types will require different types of solution techniques. So let's start with the static analysis first. Static analysis means our structure is fixed, as you see on the right hand side figure, and we have some kind of forces acting on my structure, so it will cause some kind of deformation. This means we don't have any inertia terms into it because we don't have any dynamic motion or rigid body motion, I would say, in our structure. So we can replace or remove our inertia term from the equation which I showed you in the previous slide. So I will end up with the relationship which is given something like this on the slide, as shown in the slide, and that's basically K times D equals to F, where K is the global stiffness matrix, D is the global displacement vector, and F is the global force vector. If you look at different types of methods which are generally used in the literature, without going into the details, you will hear a lot about Gauss elimination methods. You will hear about LU decompositions for small systems, and again there are many other iterative methods for large systems, for example Newton methods or something like that. If you are more interested into that, you can look at any numerical analysis book and they explain all the methods. If you're interested more on these methods, then again you can get back to me and I can create some additional videos and explaining these different types of methods being used. Okay, so if we are dealing with analysis of free vibration system, this means we are trying to solve the same system of equations which we have formulated for the whole FE model in a global coordinate system, but we are trying to solve it, finding the solution of the homogeneous equation with no forces acting onto it. So we're trying to keep everything simple, and our equation will reduce to something which is shown here. So it will be K stiffness matrix times the displacement vector plus mass matrix times the acceleration vector equals to 0, because we assume that the force equals to 0. And in this case, We commonly use methods to obtain the eigenfrequencies, as I told you, natural frequencies of the system, and eigenvectors, which will give us what sort of frequency modes or vibration modes it will be having at that frequency. And you can use Jacobi's method, for example, bisection method, QR method, subspace iterations, and Lenchos solver method. So in many of the FE softwares like Ansys and Abacus, you will find Lenchos solver is one of the mostly used method, but there are other options available as well. The last but the most difficult one is a transient response. In this case, our structures are often subjected to transient excitation. As I told you, your load is changing with time. It's a highly dynamic problem. So in such cases, for example, like earthquake, impact, shocks, etc. So in such cases, you need to use different approaches, because your time is, you have two functions now. You're solving for displacements and you're solving for time as well. So you use different types of direct integration methods. So one of the basic method which is used widely in FE softwares is the finite difference method for time stepping while solving FE equations. And there are two different types of direct integration methods. One is called the implicit method and the other one is called the explicit method. If you're using implicit method, then implicit method is more efficient for relatively slow phenomena which takes a long time, and you can't really afford to run simulations for long times. It takes a lot of time. So while explicit analysis are more efficient because for very fast phenomena such as impact and explosion. If you go into more details of these things, then you will find out that there are some conditions. For example, explicit analysis requires a very small time increment as compared to implicit, and that is why it is more suitable for short time period phenomena as compared to long phenomena which are more suited using implicit methods. Just to summarize what we have done until now, before we jump into the real numerical examples solving these different structures using FEM. So in FEM, the displacement field is expressed by displacements at nodes, and to describe those we use shape functions. Again, in the context of truss elements, we used linear elements in this course. Once the shape functions are found, we try to calculate the mass matrix and force vector. We can also obtain stiffness matrix by using shape functions, and also strain matrix can be found using shape functions, as I told you in the previous lectures. So once we have found all these, we can formulate the FE equations for any component or structure using those. So the basic ingredient of any FE analysis or how to form FE equations is to formulate the shape functions. If we know the shape functions for that solid or that geometry, rest of the process remains very much the same as I expressed in these previous videos. So in the upcoming videos, what I'm going to do is I'm going to solve a few examples starting from truss elements, and we will do a step-by-step solution of what I have tried to explain in the last few videos or so, including today's. And I will try to explain to you how all these things are applicable to structures in real time, and I will come up with some equations, some examples which are solvable by hand rather than going into the computer. But you can always go back to Abacus or Answers and try to solve the same structure, and you will find the same results out of it. So until next time, stay safe in these challenging times, and I hope you will like these videos.